Welcome back. We are now in section 7 of our journey in the coupled oscillation business that we have been looking at in this chapter. This will be actually the last section that I'm going to talk about in the string. In fact, this is already part of the wave dynamics, but it's a very good extension of what we did in part 6. Remember, in part 6 we actually studied the loaded string, where we represented the string as a massless object on which there were some masses that were small masses m that were positioned every distance d in an equidistance d along the chain, and then we found the vibration of this. Now what we would like to do is to go beyond this and to have an infinite number of masses, but of course we do not want the total mass to be infinite. So instead we want a finite total mass, and this is actually a way to represent the string itself. So this equation here on this slide is actually fairly straightforward. It allows us to move from the finite case, so n finite, to an infinite number of masses, and it will allow us to use the equation we had from the previous section for the continuous case. It's not actually very complicated, so please bear with me for a few minutes. So first of all, we want an infinite number of masses. So that means that the distance between the mass is going to be infinitesimally small. So that's what the d going to 0 means. And that also means that the total number of mass plus 1, since we keep the n fixed, so n plus 1 times d, the distance between them, is equal to L. So d is not going to be 0, but it's going to, at the limit, d times n plus 1, so something that tends to infinity times something that tends to 0 is actually here defined as the length of the object. Likewise, we want the mass to go to infinitesimally small mass, and the way we do this is because we want the density, the linear density, so the mass per meter, if you will, so the mass per d, every interval, to be constant. And of course, as you know, a mass per distance is a density, and we are going to call it rho. So it's actually very straightforward once you understand those definitions and these limiting cases, to move from the finite numbers, a number of masses, and to the infinite number of masses. And that's what we are going to do in the next few slides. And then I will end up this screencast with an example of the dynamics of a plucked string like this. Remember that the finite case, finite n, the case of finite n, was given by this solution. I remind you that R is an index that goes over all the possible normal modes. Eta R is called the normal coordinates, and we have those results here. In this slide, I'd like to attract your attention that the j should actually be an I here. I'm sorry about this mistake on this slide. It's the index I. So, okay, let's do, the I should be a j, same difference. So, let's try to see how we can impose the limit on n goes to infinity to this. So it's actually pretty straightforward. If you look at the argument of the sign, what you do, you multiply up and down by d, right? You don't do much anything by doing this. You multiply up and down by d. And when you do this, you realize that, in fact, n plus 1 times d is going to be giving us the total length, as we said in the previous slide, and j times d is a place along the chain, right? A place along the chain, which is because d is becoming infinitesimally small. J times d is actually a continuous position along the chain that we can usually call x, right? It's just the coordinates, the continuous coordinates along the chain. So that allows us to understand how to go from the finite number of masses to the continuous number of masses. So that's really nice, because now we can actually replace that argument from the equation on the top of this slide with this equation, which is actually the solution for the string which is at a continuous limit. Of course, we can also write this another way, with the understanding that we will take the real part, because the eta, the normal coordinates, are given as always by beta r e to the power I omega RT. So as you've probably noticed on the previous screencast, now the difficulty is to calculate the beta. The beta is this complex number that has two components, nu and mu, and we have all we need to do that. So the rest of the screencast will mostly be focusing on the beta. But before we go there, let's try to think about the degrees of freedom. I always recommend that we do an analysis of the number of degrees of freedom. Obviously, when we had n particles, we had n degrees of freedom in one dimension. This was the number of transverse modes. In a continuous limit, we should have an infinite number of modes. So that's a little bit of a problem, because that means that we have an infinite number of equations. But do not despair. We might have an infinite number of equations, but we also have an infinite number of initial conditions. So just to remind you, initial conditions these are conditions that we impose at time t equals 0. They are to be contrasted with boundary conditions, which are imposed on the position space. Okay, from a purely differential equation standpoint, they're very similar, right? But in physics, we talk about initial when we talk about time, and boundary when we talk about positions. So in any case, let's repeat the equation I showed you on the previous slide here. And those initial conditions are actually given at t equals 0, and then can give me the initial displacements, which are given simply by putting t equals 0 in the previous equation, knowing that beta r is mu r plus I nu r. And we can also have the initial condition on the velocity, which we given simply by the derivative of q xt with respect to time. Now, just as another reminder, we are here talking about motions. We are talking about equations of motions, which are second-order differential equations. So we need both initial conditions on the position and on the velocity. By now, I think that you are very familiar with this, but it's always a good thing to remember. So we are almost there, actually. All we need to be able to calculate now is mu r and nu r. So remember that so those two initial conditions, displacement and velocity, I'm going to repeat them on this next slide. So here they are. And we are going to use a trick. So just bear with me. We are going to multiply both the left and the right by a sine function. This sine functions, sine of s pi x over L. I mean, there's nothing wrong with this. We can certainly multiply the left and the right. We are going to then integrate both sides. Now, what's actually very nice about this is that when we integrate both sides, we are going to end up with integral of a product of sine of different arguments. And the trigonometry tells us that these functions are actually orthogonal, and this integral gives us the Kronecker delta rs times I would say a normalization factor L over 2. So this is trigonometry. It has nothing to do with the mechanics. So imagine now that you do that on the top equation on this slide. So you integrate, you multiply by sine s pi x over L, and you integrate. Now the right-hand side, as you can see, you're going to just have mu times L over 2 that's going to end up. But the left-hand side is actually exactly this. That's exactly what we wanted to look at in terms of the solution that we found in the previous two slides. So in other words, we can now express the solution qxt as a function of the initial condition. So remember, that beta r is mu r plus I nu r. Now we can calculate both mu r and nu r as those integrals that we operated on the left-hand side. There are a couple of steps here that I just said that are not on the slide. I said them, but I did not write them explicitly. So this is another good opportunity to pause the screencast and making sure that you understand how we got to that point. Now we can also look at the frequencies. The frequencies in the finite number n of mode and number n of masses was given by this. And we are going to use the same trick as before. We are going to multiply by d on we multiply by d top and bottom, and there are two things that we can do that. So first of all, we see that the prefactor, the square root, is going to, if we divide by d, we obtain m over d times d squared. So m over d is rho, and the 1 over d can go out. And the sine, again, same trick as we did before, n plus 1 times d is L, the total length of the object, and then we end up with a d. Now, of course, as we know, we are going to impose d to go to 0, because this is the distance between masses which are not continuous, so that the distance vanishes, goes to 0. And when you do that, you can very easily calculate the sign, because the sign of r pi d over 2L when d goes to 0 is, by Taylor's expansion, the first term will be r pi d over 2L. And of course, we often say in physics, magically, the d's actually cancel each other, and you don't have any worries about divided by 0. I say magically because, of course, this is not magic. The reason why it works like this is because we are trying to represent physical systems, and usually physical systems do not explode. In fact, as some famous physicists say, nature doesn't like singularities. So there are usually no singularities in solution of physical problem. But the point is that we now have the frequency of all the modes. So the modes are labeled by R, and you see that's just mode, and then the multiple of those modes, they are called harmonics. That's what we call them in music theory, for example. But the frequency is going to depend on the square root of the tension tau in the string and the density of the string. I'm going to tell you a little bit more about that when we compare to music. So you see, at the end of the day, we can summarize everything we've just done in this screencast with this page. And this is really the only page you need to solve this kind of problem, actually. It gives you the general solution. It gives you how you calculate beta r, which is obtained from the initial conditions on mu r and nu r. And you have the frequency that I just gave you on the previous slide. Now, the best way to understand how we do this, how we solve a problem like this, of course, we need to know the initial condition qx0 and q dot x0. And now in the next couple of slides, I'm going to show you an example. And for that, we are going to use a string that we are going to pluck. So it's just like it says. Like think about a violin that you are plucking in the middle. Let's say you're plucking the string in the middle. So there is a tension in the string, there is a length in the string, and you want to know, once you do that, how the string will behave. So now the pluck here is just a matter of forming a kind of a triangular function of height h. And I'm going to be frank with you. This is usually the main difficulty, is to write the initial condition that's correct. And then in this case, the correct solutions are the ones that are written here on the left-hand side. We are basically plucking, so we are not pushing. We are releasing the pluck, which has no velocity initially, so that the velocities are 0. You will see in just a second that it's going to help us a great deal to say that the velocities are zeros initially. So you have to think that you pluck and then you let it go. So initially there's no velocity. So remember that the two coefficients that we have to worry about is mu r and nu r, which I'll remind you here. These are the same as on the summary page. Good news is that the second line only yields zeros since all the initial velocities are 0. So let's get rid of this one. That's the easy one. The other one is not 0. It's actually the mu r. And we need to calculate the integral that's on the top of this slide. And the integral actually is in two parts, one from 0 to L over 2 and one from L over 2 to L, since the function qx of 0 is defined by domains. And you end up with those integral, which are integral you can do analytically, and I actually recommend that you use either symbolic calculator or look in tables. And when you do this, you can actually calculate this correctly and find that the mu r is 8h, which is the height of the pluck, divided by r squared pi squared sine r pi over 2.